Swayam Prabha. Digital India. Educated India.
Good afternoon everyone, and today we will continue with module 4 of principles of texture measurement by X-ray diffraction. In the last lecture we saw that how we can measure alpha and beta and obtain intensities at various alpha and beta point to measure the whole pole figure for a particular HKL plane. In this lecture, this is lecture number 26, we will show various texture goniometer components. So, the concepts that will be covered in this lecture are history of the pole figure development, and then we will carry out with various components of texture goniometer system, and then we will look into detectors in little detail. So, you see, when we look into the history of the pole figures, it was Weber which in 1924 generated the first pole figure in Berlin University in Germany. So, he did it by evaluating the inhomogeneous intensity distribution along the Debye-Scherrer rings. In 1948, Decker and Norton separately they developed they did it separately. They developed the texture goniometer and the Geiger counters. So, Geiger counters are the the phosphor screens in which the intensity of the diffracted texture intensity beams are measured. So, in 1949 modern texture analysis method by Schulz was introduced, and we discussed in very detail what is Schulz reflection method for pole figure measurements using X-rays. So, in 1960 neutron diffraction was introduced and was utilized to measure pole figure for transmission geometry, goniometer geometry, right. And nowadays you see computer controlled and automated softwares are present, which are in sync with hardware. So, hardware and integrated software programs are there, which are available for texture measurements, their analysis and all the corrections that are needed to be done. So, basically while we do this kind of texture analysis, we use basically HKL Oxford Instruments software, which is HKL or TSL EDAX, and we always use ATEX, which is a free software given by Benoit Bouchir and Jean-Jacques Fundenberger of University of Lorraine, Metz, France. And at the same time there is another software which I have not mentioned here, forgot to mention here, that is the M.Tech software to measure this X-ray diffraction, which is also a free software available in the internet. So, these are all different kinds of software tools which can be used for the measurements, mainly HKL and TSL can be used for measurements, because it comes integrated with the SEM and EBSD, and both of them are mostly used for the SEM EBSD case, whereas for XRD texture measurements there are specific softwares from different companies like Pan Analytical, Bruker or other companies, and then this ATEX can be used for measuring both pole figures obtained from X-ray diffraction and also from electron backscatter diffraction in an scanning electron microscope, and even in I think they are developing it for the transmission electron microscope also. M.Techs on the other hand are analysis software for X-ray texture pole figures. So, this figure is a typical texture goniometer of the history. So, you see this is a texture goniometer. This figure is adapted from the book of Introduction to Texture Analysis by Olaf Egler and Valerie Randall, and this is the texture goniometer which is was basically present in RWTH Aachen in Germany. So, Institute of Metallurgical and Metal Physics. So, you can see that how big the Eulerian cradle was, and we can observe that the detector and the the source of the X-ray beam. And if we look into details of this texture goniometer, here is another figure that I would like to show, and this figure is basically a picture taken and adapted from Introduction of Texture book by Hatherley and Hutchinson. So, this is basically a very old model, maybe the oldest model of texture goniometer. The figure can be used to clearly depict all the components in the in this diffractometer, and this is the diffractometer which is based on reflection mode, that is Schulz diffraction method, right. So, you see this part of the goniometer is basically the source of the monochromatic X-ray beam, and so the monochromatic X-ray beam basically comes out here, and it goes to two slits which might be present inside here, and they are very narrow horizontal and vertical divergence slits. So, this goes and it goes to the sample which is kept here on the sample holder 4, right, and you can see that it consists of a major circle which is basically known as the goniometer circle and is given by zeta rotation, right. We must remember that in the reflection mode the zeta rotation is equal to 90 degree minus alpha, which is actually done along TD, and it is done zeta is the right hand thumb rule based rotation, right. So, zeta rotation is there, and then it goes, if the X-ray beam goes and hits the sample and it diffracts and it goes to the detector here, the detector here. So, the detector system could be a Geiger counter, and nowadays it could be a point detector or a line detector or a surface detector, right. And before it goes to the detector, it has to pass through the receiving slits and anti-scattering slits, so that the width of the beam reduces. Now, this figure is the photograph taken of the most latest X-ray texture goniometer that has been installed recently in the Central Research Facility of Indian Institute of Technology, Kharagpur. You can see the difference between the oldest model and the newest model here, and you can see that in the newest model the source of the X-ray has become so small and so sophisticated. Of course, it has the divergence slits and the technique or the mechanism remains the same. It has the 4 axis 2 theta omega zeta phi goniometer, and you can see that it has the sample holder with a you see a translational stage, one's translational and in this direction and another translational outside and inside of the screen, right. You can see the presence of the receiving and the anti-scattering slit, and in place of point detector which was present in the old models. Now, surface detectors are being present, which makes the pole figure measurement faster. So, with the advent of the technology, the pole figure measurements, as you know that we have to measure each pole figure h k l for a particular theta, fixing omega in such a way, so that for that particular theta, making that omega equal to 0, and then measuring that h k l plane, like that all 2 or 3 or 4 h k l planes has to be measured, and all the measurements basically goes from 0 to 70 degrees, and it cannot go from 0 to 90 degree in alpha, that is the zeta rotation, but we will show why it is not up to 0 to 90 degree, because of the defocusing status, where the incident beam becomes almost parallel to the sample surface. We will talk about that later. So, this is what about the different kinds of components that are present in the X-ray texture goniometer. Now, you see that in order to obtain the peak, as I said, the omega is basically rotated, so that it goes to that theta or 2 theta for that particular h k l plane to get that Bragg angles reflection, right. You see that usually what happens when we do a different kind of samples, and we have samples which may have residual stresses, or which have some stresses, so that its d is somewhere elongated or it is compacted. So, in order to obtain to see the quality of the crystal, means where actually the theta lies for that particular h k l plane, a rocking curve is usually done. The rocking curve is basically nothing but there along r d, the omega is given, a slight rotation along r d is given to see the exact peak position of the sample, and you see that if this is given, then the theta basically changes a little by delta theta, and that is how we get the exact peak position of the sample for the any particular h k l plane which may be required. Now, this figure basically shows this rocking curve. At the same time, we are showing this along with a linear position sensitive detector. You see, a linear position sensitive detector can detect has a larger, it has a length, it is one dimensional, it has a length. So, it can take intensities from more than one h k l planes which are diffracting at different thetas, right, and this diffraction may occur, and this may not follow the Bragg-Brantonose focusing condition, but still it will diffract. We will come to that, but you see that here the incident beam, remember that this incident beam is shown to be a single line, but it is coming like a point parallel, but it is not like that, it is a divergent incident beam, and then it seems like it is divergent diffracted beam, but it is not like that, it is a convergent diffracted beam. But you see why the different angle has been shown, this different angle has been shown to show that if the diffraction can occur in 3 different planes, 3 different h k l planes which are closer and maybe in a range of 5 to 10 degrees from each other, and then the linear position sensitive detector may detect all these 3 intensities and may be able to separate out these 3 intensities. So, at a single go one can measure 3 pole figures at the same time, but there could be inherent difficulties that we will talk about in the later slides. Now, you see the 1D position sensitive detector comes with a multi channel analyzer, and the intensity distribution of the diffraction peaks in different locations of this position sensitive detector is basically noted down by this multi channel analyzer. At the same time, in few cases linear silicon strip detectors are also used. Now, here is a figure which we have shown, though we have discussed this in quite a detail in the last lecture, but still I think that it is needed to have a little bit of more understanding in terms of presence of a linear position sensitive detector. So, if you see that if there is a X-ray source and it gives a divergent beam like this, and then there is a divergent beam which is a convergent beam, diffracted beam, which goes to the detector, and if it is a point detector, it goes exactly to this point. So, that it is detecting this. Now, you see that the incident beam and the diffracted beam has a bisector, and this bisector is exactly like this, and this bisector is at the initial position when alpha is 0 and beta is 0, that means zeta is 0 and phi is 0. Then at this position k, that bisector is basically parallel to the ND, right. And when under such condition, this we should always remember that when we measure a certain plane by rotating alpha beta, we always measure that plane which is perpendicular to that bisector k, and therefore, we get the information for that HKL plane for every alpha and beta possible. So, if this is a divergent beam and it is a convergent beam, then if this is the, and if this is always kept constant in such a way that we are always measuring that particular intensity which is corresponding to this k bisector, then this position, this point always comes in the Bragg-Brentano focusing circle, right. So, the Bragg-Brentano focusing circle is such a way, so that in a point detector, the position where the the intensity of the X-ray beam basically get focused is the Bragg-Brentano focusing circle. Now, you see that if this is the Goniometer circle, this Goniometer circle basically represents the circle where and if you say that if this is, you see R d, the along R d, the omega axis omega is rotated. Now, omega is rotated in such a way, so that we first fix it for that particular theta. So, that now the Bragg-Brentano's focusing circle is being fixed for that particular theta, for that particular HKL plane, which will get focused here, right. Now, the point is that when there is a presence of a linear position sensitive detector, then what will happen, that even if there are other HKL planes, say H 1 K 1 L 1 plane, H 2 K 2 L 2 plane, then also these two planes may get intensity peaks here. So, at the same time, you see a linear position sensitive detector can be used to measure the positions of three simultaneous plane, the one which is having the Bragg-Brentano focus and the two others which does not have. So, you see that the omega of this 4 axis goniometer is is rocked or rotated, and so that it gets to the particular Bragg angle theta, and then it is made equal to 0. And this makes this this k, the bisector, which is which lies in this zeta circle, and this zeta circle becomes symmetric, means becomes the bisector which consists the k of this incident and the diffracted beam, right. So, this zeta circle, this one, if you think that a circle is there, right, in this axis which is the k. So, if we use a linear position sensitive detector, then there is a deviation from the Bragg-Brentano focusing condition for this case, because the linear position sensitive detector is actually kept tangential to the this goniometer circle, and therefore, you see that this H 1 K 1 L 1 and this H 2 K 2 L 2 are not in the focusing condition. Now, one can say that one can use a curved linear, not linear 1D position sensitive detector, which should go through the Bragg-Brentano focusing circle, but then also you see that even if it is instead of linear, even if it is you see what you call a curved position sensitive detector, the Bragg-Brentano it all the three focused diffracted intensity beams from the three different HKL planes of three different thetas may lie at the Bragg-Brentano focusing circle and the detector also may lie at the Bragg-Brentano focusing circle, but then also the k between these 3 different beams may not remain same and the goniometer circle may not follow the all the time the Bragg-Brentano focusing condition. So, you see as I have stated earlier that you see that the X-ray goniometer basically rotates zeta and phi, that is alpha and beta. So, basically a linear position sensitive detector has a viewing angle of 5 to 10 degrees and it must have a very good angular resolution of 0.1 degrees, and so that it can record individual H1 K1 L1 H2 K2 L2 H3 K3 L3 for theta 1 theta 2 theta 3 all different Bragg angles for these 3 different HKL planes, and this must include the must include the peak broadening at high tilt angles and also should have it should provide the separation between the overlapping peaks. So, as I said, the curve PSD detectors are also coming up in this case, but you see that as I said that 2 problems arise when we basically increase the deviation from the Bragg-Brentano focusing condition. The first condition is that the first problem is that the Bragg-Brentano focusing condition is violated. So, zeta circle is now inclined to the omega and to the bisector of the bisector, and then it will lead to peak broadening, right, peak broadening. Secondly, as the omega, zeta and phi has to be converted into alpha and beta poles, and now the alpha is always less than omega and the you see the diffracting poles cannot be brought in coincidence with the bisector, right. So, the diffracting poles and is not in coincidence with the bisector. So, it will give the correct diffraction and softwares can be used to correct it, but you see it may result in non measured blind spot area at the center of the pole figure, and with the increasing this deviation of alpha and omega, what will happen, that means with the increase in the omega, the size of the blind spot in at the center of the pole figure will increase, right. So, okay. On the other hand, in the reflection mode, area detectors can are coming up into with coming up to measure 2 or 3 different HKL planes simultaneously with the more and more advent and the development in the science and technology. So, you can see that the pole figure measurement, this is an what you call hypothetical diagram which shows us steel samples and a sample which has RD above, ND here and TD this side. In the reflection geometry same, but this time the incident beam is coming from this direction and here is the area detector present, and in this case what has happened that you see one can measure, you see hypothetically this is just not to measure by scale diagram which shows intensity measured by 110 and 200 all together in a case in using an area detector. So, for this intensity points may look something like this in the phosphor screen. So, for a fixed position of the pole figure angles omega and alpha, a large portion of the pole figure can be scanned with one beta scan using such kind of an area detector, right. So, we can conclude here that the major components of texture goniometer that we studied today is the monochromatic X-ray source, horizontal divergence slit, vertical divergence slit, sample holder, a goniometer circle, right, Eulerian cadre, receiving slit, anti-scattering slit and the detection system. The Bragg-Brentano focusing condition for reflection geometry is required to be satisfied to obtain texture intensity for the alpha beta scan, right. Violation of Bragg-Brentano focusing condition occurs while measuring multiple diffraction from different HKL planes in linear PSD, as blind areas at the center of the pole figure will start to evolve, and it will increase as omega is increased compared to alpha. So, you see the curved 1D and 2D detectors, means the 1D detector curved position sensitive detector, and 2D means the surface, but curved position sensitive detector could be used to, means can be utilized to maintain the diffracted X-ray beam focused in the Bragg-Brentano focusing circle, but still there would be problem to maintain it in the goniometer circle, right. So, thank you very much for this class.